Let's prove that if we are trying to maximize the heat transfer occurring on a rectangular flat plate with a fixed area, we want to orient the flow on the longer edge. Now, the Nusselt number that we'll be using for the rectangular flat plate, that's equal to 0.332 multiplied by the Reynolds number to the 1/2 power, and that's multiplied by the Prandtl number to the 1/3 power. Let's draw our flat plate that we're talking about maximizing the heat transfer over. So the flow is going to hit the plate. It's going to create a boundary layer. And that boundary layer is going to have length. There will also be a depth corresponding to the plate that we want to consider, and we'll call that x1. From here, let's find the units that we're using in our Nusselt number. Now, our Nusselt number is actually the ratio of convective heat transfer to conductive heat transfer. And that means that is equal to the coefficient of convective heat transfer multiplied by x over our coefficient for conductive heat transfer. Our Reynolds number that we're using, that is going to be our density multiplied by velocity by the depth over viscosity. Finally, our Prandtl number, specifically the relationship between momentum, diffusivity, and thermal diffusivity. At this point, you should understand that these two are equal to the viscosity divided by the density over the conductive heat transfer coefficient divided by our heat constant multiplied by our density. Now let's simplify this. So we get our viscosity over our density multiplied by that constant. This is multiplied by Cp times P, cancel out certain units, and we get our viscosity multiplied by our heat capacity divided by our conductive heat transfer coefficient. Now for this problem, we're looking at maximizing our heat transfer, and that's going to be our convective heat transfer. So we want this to be the largest number possible, which means when we plug it back into this equation, we're going to be solving for that H, our heat transfer our convective heat transfer coefficient. So let's plug everything in. We have our Hx over K is equal to 0.332, our Reynolds number, which is PVx over mu, to the 1/2 power multiplied by our Prandtl number, which is our viscosity multiplied by our heat capacity over our thermal diffusivity, our conductive heat transfer coefficient, honestly, to the 1/3 power. So let's solve for our H, and so you'll multiply everything by K and divide it by X. Just put that on the outside. This is the equation that we're looking at right now in order to find how to maximize the heat transfer coefficient. Now let's multiply everything and expand it out. So we have K to the 1 power, X to the -1 power, 0.332 multiplied by density to the 1/2 power, velocity to the 1/2 power, X to the 1/2 power, then mu to the -1/2 power, multiplied by our viscosity to the 1/3, heat capacity to the 1/3, and our constant to the -1/3. Let's combine our exponents. Start with K, and these two K's help each other out a little, so it becomes K to the 2/3. We'll put that over here for now. And we have our x, and there's another x right here, and that becomes x to the -1/2 power. Then we have our 0.332, our density to the 1/2, our velocity to the 1/2. Those are not going to change over our mu to the 1/2. We're just going to keep these. We're going to keep the mu's separated. It's just easier to think that way. And our heat capacity. So let's look at all of these components and let's see what affects our heat transfer coefficient the most. You'll notice that x is to the -1/2 power. So as the depth increases on our plate, our H will decrease, our heat transfer coefficient will decrease, and that's not what we're looking for. We're trying to maximize it. So the reason that we want the flow to go along the long side of the plate is because then the depth will become shorter, right? Let's visualize this. So we have a plate, we put it this way, say this is 5 inches and this is 2 inches. Our flow can go 5 whole inches in depth, and that decreases our heat transfer coefficient, which ultimately decreases our max, it doesn't create the maximum heat transfer. We were to orient the plate on its long edge and allow the flow to go on the long edge of the plate. So this is 5 inches and this is 2 inches. Now the flow only reaches a depth of 2 inches. So our heat transfer coefficient is going to be the maximum when we're looking at the plate on the long edge, where the flow is hitting the long edge.